Welcome to the video for section 6.2, and this is one-to-one functions and inverse functions. Mainly, they go hand in hand due to the fact that one-to-one functions allow for inverse functions. Now, we have looked at what makes a function. Now what we're going to look at is what makes a one-to-one function. And so we begin with example number 1. And the question is, determine whether or not the function is one-to-one. Well, we can look at it very easily and see, since the x's do not repeat, it is a function. But how do we know that it is one-to-one? Well, in order for it to be one-to-one, the y values cannot repeat. And so if we look at this, we notice that -8 repeats 3 different times. And so that would automatically mean, no, this is not one-to-one. So in order for a function to be one-to-one, the y values cannot repeat. Number 2. Now, whenever we're testing for a function, we use the vertical line test. Well, to determine whether or not a function is one-to-one, we use a horizontal line test, and it is exactly the same as the vertical line test. Is there any horizontal line whatsoever that ever crosses the graph in more than one place? And if we look at number 2, with the graph like this, there's never a case where a horizontal line will cross the graph in 2 different places. So since it never crosses in more than one place, the answer is yes, it is a one-to-one function. Number 3, to find the inverse of the function, all we really have to do is switch x and y, and that is what's really important about this section. Switch x and y, and then we're going to be good. So number 3, whenever we've got points, all we have to do is switch the x and y, so it becomes 6, 1, 7, -1, 8, -3, and 9, -5. We are also asked what's the domain and what's the range. So now the domain would become what used to be the y's, so that'd be 6, 7, 8, and 9. And the range was what the domain used to be. So that would be -5, -3, -1, and 1. Now, how do inverses look on a graph? And we are asked to graph the function, and the function is f of x equals the square root of x plus 5. So we have to go back a little bit. We have to remember that this is the square root function, and since the plus 5 is directly connected to the x, it doesn't behave, so it will go to the left by 5. So what we're going to get will be these points. Shift it over 5 to the left, so it's going to be -5, 0, -4, 1, -1, 2, -4, 3, and we could have more if we really needed it. And we need to remember that the square root curve looks like that. Now we are asked to also graph its inverse, which means switch x and y. Now the easiest way to switch x and y is to reflect this graph over the line y equals x, because remember, the whole trick is we're going to switch y for x. And so what we would get is we would get the points 0, -5, 1, -4, 2, -1, 3, 4. graph is slightly off because that point should really be there. And we get something that looks like this. And notice that truly these two curves here are reflected, if my graph were more accurate, would be reflected over the line y equals x. And so this is f of x. This graph down here is the inverse of x, and that's how we show that. F raised to the negative 1 of x. So this is the easiest way to graph a function along with its inverse on the same set of axes. Continuing, 5 and 6 ask us to decide whether or not the functions are inverses of each other. And what we need to do sorry about that, my microphone just sort of flew away. When we need to decide whether or not the functions are inverses of each other, we have to go back to last section where we were taking the composition, and in order for two functions to be inverses of each other, whenever you take the compositions, they both need to equal x. Remember that I did mention that a little bit, or at that time. So the first thing we're going to do is take f composed with g, which is f of 1/5 x plus 1, and then that would mean it's going to be 5 times x. Well, x in this time is 1/5 x plus 1 minus 5. And let's see what we get. 5 times 1/5 x is x. 5 times 1 is 5. Minus 5. X plus 5 minus 5 is x. So at least that part of it is okay. And g composed with f would be g of, okay, once again, f is 5x minus 5. And so into g we're going to put in 1/5, and instead of x we're going to put in 5x minus 5 plus 1. And distributing the 1/5 we get x minus 1, then the plus 1, and x minus 1 plus 1 is x. And so the answer is yes, these are inverses of each other because their compositions in both directions equals x. Now also, if we look at them, 5x minus 5 and 1/5 x plus 1, we can possibly see how those are opposites of each other. It's not extremely obvious, but perhaps it's not too far of a stretch. Example number 6 is the exact same type of problem, and so I want to take f composed with g, which is f of, okay, 5x plus 1 over x, which will equal 1 over, okay, I need to put 5x plus 1 over x, remembering that I'm putting these inside parentheses here, plus 5. And so we need to really try and straighten this up. So I'm going to do common denominators down below. So that'll be 5x plus 1 over x plus 5x over x, all under 1. And so I know that I've got a 1 over, I know the common denominator is x, and 5x plus 1 plus 5x is 10x plus 1. And 1 over this would equal x over 10x plus 1. And it's at this point, regardless of how hard I try, I'm never going to get this equal to 0. Or to x, because this would have to equal 1, and I have no justification to set it equal to 1. So this, I can say, no, they are not inverses of each other. And once again, to me, number 6, they look just as much like inverses as does number 5. So you can't just go by looks. You really need to go through and figure out, okay, here's the rule. If they turn to be an x, then great. If not, then pretty much we're done. Suppose it's our job to find the actual inverse. We need to remember, switch the x's and the y's. So number 7, the function is 7x minus 8. First thing we have to do is get our y. Well, that would be y equals 7x minus 8. Switch the x's and the y's. So we get x equals 7y minus 8. And then finally solve for y. So I'm going to add 8 to both sides and divide everything through by 7. So y would equal 1/7 x plus 8/7. I look at what I think is my inverse, which we say the inverse function is equal to 1/7 x plus 8/7. And I look, does this look like the opposite or the inverse of this? I can certainly argue yes, it appears like it would work. If we really wanted to, we could take this with this, composed with that, and we should end up with x. Number 8, f of x is equal to x cubed plus 1. First thing we need to do is get a y. So y equals x cubed plus 1. Switch x and y, so we get x equals y cubed plus 1. And then solve for y. So I'm going to subtract 1 from both sides, and then take the cubed root of both sides. And then rewrite it as the inverse function. The inverse function is the cubed root of x minus 1. Remember, f raised to the negative first x is the inverse function, is the cubed root of x minus 1. Now here, this to me appears to be much more the inverse of the original as any of them that we've looked at so far. Example number 9, f of x equals the quantity x minus 4 cubed. We need a y, so y equals the quantity x minus 4 cubed. Switch the x's and the y's, so x equals y minus 4, that's a 4 not a y, cubed. And we need to solve for y, so the first thing I'm going to have to do is take the cubed root of both sides. So I get y minus 4 equals the cubed root of x, and then add 4 to both sides, so that the cubed root of x, and then plus 4 is not under the cubed root. And then finally, rewriting this into the inverse function form, we get the cubed root of x plus 4. And here, once again, I can see our inverse being the inverse of that, but it's not, there's no way to go directly from the function to its inverse. Example number 10 is the final problem in this particular group of problems. F of x equals negative 5x plus 9 over negative 5x minus 8. So we need to get a y value in there. So we just change the f of x to a y. Switch the x's and y's around. This one's not going to be quite as much fun, but realize the next thing we can do is we can multiply both sides by negative 5y minus 8. And so that'll be x times negative 5y minus 8 equals negative 5y plus 9. Distribute the x, negative 5xy minus 8x equals negative 5y plus 9. We need to get all the y's to one side and most of the x's. We're going to have to keep this the first x over here for temporarily, but I can add 5y to both sides. And then I can add 8x to both sides. Rather lengthy one, but now since we have a problem because we have two y's. So what we really need to do is we need to factor out that y, leaving negative 5x plus 5 whenever I factor that out. And then I can divide by this whole thing. I can divide by negative 5x plus 5 on both sides, and I will get 8x plus 9 over negative 5x plus 5. And so I've solved for y, so the inverse function hopefully is 8x plus 9 over negative 5x plus 5. And if you look at this, I think you would find it real difficult to say, oh yeah, that obviously is the inverse of the original function. But realize, you know what? Sometimes things just are not all that obvious. Example 11. We are told the function is 1 to 1. We need to state the domain and the range of f and f negative 1. Well, here's the nice thing about it is, remember that the domain of one is the range of the other. And so once we find the domain and the range of one, all we have to do is switch them around and those become the domain and the range of the inverse. So let's find the domain and the range of f. The domain, the only place that it's not allowed is when 2x minus 5 equals 0, because that's what's in the denominator. So solving for x, we get 2x equals 5, x equals 5 halves. And so the domain for f would be everything but 5 halves. So that'd be negative infinity all the way up to 5 halves, along with 5 halves to infinity. Now the range, we have to determine, are there any values that it will never equal? Well, we have to think, will this ever equal 0? And the answer is no, because the only time that a rational expression or a rational number will equal 0 is if the numerator equals 0. And so it will never equal 0, and that is the only value that it never will equal, because we could get infinitely big, we could get infinitely small, and that would contain the entire gamut except for 0. And so the range is everything but 0. So we get this. Now the really nice thing, that's for f. The inverse, we don't have to do any thinking whatsoever. The domain now becomes everything but 0. And the range becomes everything but 5 halves. And the 12th and final example for this section. Find a formula for the inverse of the function described below. Okay, we have f of x equals 9/5 x plus 32. and this is the one that changes from Celsius to Fahrenheit. So when we find the inverse, we're actually going to be finding the Fahrenheit to Celsius. And since all we have to do is find the inverse, the first thing we're going to do is get a y. The process is exactly the same. Just because it's in a word problem doesn't mean anything. Switch the x and the y. And solve for y. I'm going to subtract 32. And multiply by 5/9. And then rewrite it in its inverse form. F inverse of x is 5/9 times x minus 32. Now this is the more common way to show it, but it would certainly be okay to go ahead and distribute this. But since this is the most common way that it's seen, I'm going to stop right here.